Hey everyone, my name is Kaylen Woods and today we're going to be talking about Martian space weather. So I go to school for meteorology and atmospheric science, and I'm also minoring in astronomy and astrophysics. And combined together, these two seemingly different sciences have actually a lot in common, and that commonality is called space weather. So a lot of people know about Mars. It's a really cool planet. It's our neighbor planet, and there's a lot of interesting science going on over there. They're sending the Mars rover there, the 2020 rover, and they're also going to be sending astronauts soon. So it's really important that we know as much information on Martian space weather as possible. What a lot of people don't know is what space weather really is, and I didn't even know it until I went to college and I learned more about it. So we have Earth. And the Earth is really dependent upon the sun. I mean, we need it to live. It grows our food for us, and it gives us energy, and it's really great, and we view it that way. But there's also some crazy stuff that happens at the sun too. It spews out some really dangerous stuff that we need to protect ourselves from because we don't want to have anything damaged. The sun can spew out radiation, and it can also spew out a lot of energetic particles, and some of these particles we like to call the solar wind. So it comes out of the sun and it heads toward Earth, and on its way it can impact other things like satellites that are hanging out in space, or astronauts that are doing important missions, like for example on the moon maybe. But once it gets to Earth, it's met by a magnetosphere. So it's kind of like a protective bubble around the Earth that keeps us safe. And the magnetosphere forms around Earth, and then it drifts off into a tail in the end. It just kind of extends for a while. It's just the shape of how it works. So when the solar wind is met by Earth's magnetosphere, it can't really damage what's on Earth. Sometimes bad things can happen, but it's certainly not as bad as it would have been if we would not have a magnetosphere at all. So our magnetosphere keeps the atmosphere safe because sometimes when solar wind energetic particles come in, it can strip away atmospheres of planets. So we definitely don't want that to happen. We want to make sure life on Earth is all good to go. But this solar wind, as it travels through space, it of course will impact other planets as well, like all the ones that we know. For example, Mars gets impacted a lot by space weather too. But Mars gets impacted in a different way than it would on Earth or Venus or other planets, because Mars doesn't have the same sort of magnetosphere that we have seen on Earth. Scientists say that Mars has a really unique situation in that it's kind of a hybrid of what we see on Earth with a magnetosphere and what we see on planets with absolutely no magnetosphere at all. It's kind of in between, but it's still really confusing because it's not a certain answer. See, what happens on Mars is that there's things called crustal magnetic fields. So for example, in small patches of Mars, say right here in the center, there might be a crustal magnetic field. And if you turn the planet, there might be one down here. They're all around the Earth in different patches. It's a patchwork of magnetic fields. And so instead of having one global magnetic field, you have little patches, which influences what the magnetosphere is going to look like because it's very dependent on the topography of the patches. So another interesting fact to know is that these crustal fields actually rotate when Mars rotates through space. So they'll stay in their exact spot all the time. And that makes for some really interesting science because, again, as the solar wind comes in and starts to impact Mars, it's met with a different looking magnetosphere depending on the time or the orientation of the crustal fields. So that leaves up a lot of questions. And so there's a really interesting tool out there. It's a satellite called MAVEN, and I actually used it last summer when I was at an internship to study what happens in the magnetotail of Mars, because there's some really interesting stuff that happens back there. What we observed was that in the Martian magnetotail, there is two lobes, and these lobes, instead of just being normal and straight throughout the rest of the magnetotail, they're actually twisted around one another, and that's something that nobody expected. And so this twisting could be modeled by the data we saw by MAVEN, but there still wasn't a concrete answer. The solution to this really tricky problem is something called magnetic reconnection, and we're still learning about this stuff to this day, so there's a lot left to explore, so definitely look it up if you're interested. But magnetic reconnection is kind of exactly what you think it is. It's the connection of two different magnetic field lines from maybe different sources. So we have the magnetic field lines from the sun, and we also have the magnetic field lines from Mars. And so these might connect. And when that happens, there's a lot of energy transfer going on. It's a crazy event, and it is so crazy that it can actually change the topography of the field lines. So there might be field lines that start at Mars and then just go off into space. They're not really connected to anything, and that can lead to a lot of interesting science. So if you're interested in it, that's all the time I have. Take a look, but it was so fun to talk about space weather with you. Bye!
Hi, my name is Lindsey Weiser, and I'm an intern at NASA Headquarters. I studied engineering and planetary science at Johns Hopkins, and I'll be starting graduate school at Arizona State University. What I study the most are exoplanets, or planets outside of our solar system. So that's what I'm excited to talk about. I'll share a little bit about how we search for these planets and some of why they're so exciting. In our solar system, there are 8 planets, with Earth being the third from our sun. But if you look up at the night sky, you can see countless stars. The longer you stare, the more you'll see. Now picture this. Each star is its own sun, and many of them have their own planets. We call these planets outside of our solar system exoplanets. There are different ways we can search for these exoplanets and start to learn about what they're like, so I'll talk about just a few. One way is by watching for wobbling stars. As a planet orbits its star, the gravity between the two bodies causes the star to wobble just a little bit as the planet tugs on the star, and that slight wobble can be detected with big telescopes. Another way is to spot exoplanets with the transit method. A transit happens when a planet passes between us and a star we're observing. When this happens, the planet will block some of the starlight and actually cause the star to dim by a measurable amount. Picture a fly passing in front of a light bulb. Each time the planet orbits its star, it will transit again. An interesting benefit of this method is that a sliver of starlight also passes through the planet's atmosphere around the outer edge of the planet. By observing which wavelengths or colors of light make it through the atmosphere and which ones are blocked, we can start to figure out what the exoplanet atmosphere is made of. Earth's atmosphere, for example, is mostly nitrogen and oxygen. A third method of spotting exoplanets is direct imaging, which is just taking a picture of the planet itself. But taking a picture of exoplanets is actually really hard because the light from their star is so bright that it overwhelms the planet. So we have to block out the starlight. Once the star is covered, planets orbiting around it can be revealed. We're still learning about the best ways to do this, but we're getting better at it. Thousands of planets of all shapes, sizes, and temperatures are being discovered, and some of them might even be similar to Earth. As we continue to explore other worlds and improve our technology for observing them, we may one day find evidence of another planet capable of supporting life, a habitable planet. Life as we know it on Earth requires liquid water to survive. So in the search for other habitable worlds, we look for planets on which the temperature is just right for liquid water to exist on the surface. Not too hot and not too cold. These planets must be at the right distance from their star, a distance we call the habitable zone. In our solar system, Earth is in the habitable zone. A planet like Mercury is much closer to the sun and is therefore too hot for liquid water. The outer planets are just too cold. So why do we study exoplanets? Well, for me, it's because Earth is one planet of many. There's so much more out there, and by exploring other worlds, we can start to understand and appreciate our own planet a little bit more. Thank you for listening, and I hope you learned something. Let's keep exploring.